about astrophysics, and it's a pleasure for me to introduce Valerio. Valerio graduated and got his PhD at the University of Salerno, and he spent 3 years at the theory division at CERN, and working on string cosmology with Gabriele Veneziano, the father of the string theory. And he invented a new method to describe the gravitational lensing by supermassive black holes. And now he finally moved to extrasolar planets, which is the object of this talk. And he is the manager of the Astronomical Observatory of the University of Salerno.
Okay, thank you very much for the invitation. Is this working? Okay, I will use this one. Okay, so my talk will be about extrasolar planets. So this is one of the youngest fields in astrophysics, actually, because it's only 20 years or so that we know that there are extrasolar planets, actually. And it is a very fascinating field, because I think that many of us grew with reading or watching science fiction movies in which humanity was exploring distant worlds. So now it's a very special era in which we are actually seeing these distant worlds, the real distant worlds, and we are starting to learn how they look like. Okay, so as I told you, the first extrasolar planet was discovered in 1995 by Meyer Kelot of the Observatory of Geneva. And they discovered the first extrasolar planet orbiting around the star 51 Pegasi. Actually, this was the first planet found outside the solar system. But instead of being something similar to what we knew about planets of the solar system, such as rocky planets inside and gas giants in the outer regions of the planetary system, this planet was similar to Jupiter, but at a distance of only 0.05 astronomical units. The astronomical unit is the distance of the Earth to the Sun. So this is only the 5% of the distance of the Earth to the Sun. So there is nothing like that in the solar system. We have no giant planets so close to the Sun. So this is something completely different of what we expected to find. And so this opened a lot of questions about the variety of planets in the universe. The method they used in order to detect this planet was the radial velocity method. So in this case, this is just based on spectroscopy, because we know that if we have a source that is moving far away from us, then there is the Doppler shift. So the emission will be redshifted. If the source is moving toward us, then the emission will be blue shifted. But in this case, we are not seeing the planet directly. We are looking at the star. And so what we see is the very small oscillation of the star around the center of mass of the system. So both the planet and the star actually are moving around the common center of mass. And so what we are seeing is just a small oscillation of the star around the center of mass. And so this is what we are seeing there. Is this possible? No. Okay, yeah. Okay, now it's working. Okay, so this is just a plot of the Doppler shift as a function of time, and we can see that this periodic signal that is a signature of the existence of the planet moving around the star. Okay. The second method that was introduced was the transit method. This is much more simpler, actually, because in this case we are just detecting the transit of a planet in front of the star. What we are seeing is actually a drop in the flux of the star, because a small part of the star is actually obscured by the presence of the planet. So the light from this portion of the star is blocked. That's why we are observing this drop in the flux of the star. So when the planet moves in front of the disk of the star, we have this drop. Then at this point, the planet moves away from the star, and so we recover the original flux of the star. And in this case, of course, the power of the signal is actually proportional to the ratio of the areas of the planet disk and the star disk. So this is proportional to the square of the radii of the planet and the star. So in the case of a Jupiter-like planet, Jupiter as a radius is just 1/10 of the radius of the Sun. So squaring, we obtain a signal of 1%. So we have to detect a drop of 1% in the flux of the star. If we consider an Earth like a planet in front of a Sun-like star, we have a signal that is very, very low, 0.008%. So it's very difficult. We need a very accurate photometry in order to detect such low signals. If we are lucky, we can combine the transit measure with radial velocity measurements. And so in this case, we can have a complete solution of the system. We can learn the mass, the radius, the density of the planet, and so we can start to see how the planet looks like, if it is rocky, if it is gaseous, or so. We can know the distance from the star, the orbital period, and the equilibrium temperature. Because if we know the distance from the star, we can assess the temperature of the planet. So the protagonist of the last few years has been the Kepler satellite. This was a space telescope that was pointed on the same field for many years, and in this case, this telescope discovered about 2,000 extrasolar planets in this field. So most of the planets we know at present time come from the Kepler campaign. And for example, it also discovered the first habitable planet in 2015. It discovered the first circumbinary planet, and so many different worlds. Of all these planets, actually only 55 are potentially habitable. Now, let's try to understand what habitable means, actually. So, what are the requirements for a planet to be declared habitable? Of course, we have to extrapolate what we know from the existence of life on Earth. In principle, we can exclude gaseous planets because the gaseous planets are dominated by convective motions. So, in practice, if we have a molecule in one layer of the atmosphere, this is dragged in the upper atmospheres and then it falls down. So it will face many different environments. So it's not a stable environment where life can be generated. So we have to exclude the gaseous planet. In practice, this confines us below 5 Earth masses. And then the other requirement is that the surface temperature must allow the presence of liquid water, just because we know that life in the on the Earth needs water. And there are some reasons to believe that this is a quite general requirement, because we don't know any other environment in which chemical reactions have a rate similar to what we have in liquid water. So in practice, in all other environments, we would need much more time to develop the same chemistry. So in practice, if we in this chart we can see a lot of gaseous planets which are excluded by the first criterion, even if they are in the potentially habitable zone, because in the green stripe here there would be the presence of liquid water, but if we have gaseous planets, these would be excluded. But in this chart we can also see blue worlds, which are actually rocky planets, and that if they fall in the green in the green zone here, they can host liquid water, so they are potentially habitable according to this criteria. For example, in this chart we have the Earth, our own planet here, Mars, which is on the outer boundary of the habitable zone. Venus is too hot here in the red region, so in this case there will be no possible life. Okay, so this is another map of the known habitable planets of the sky. Of course, most of them are concentrated here because this was the field that was observed by the Kepler satellite. Now, among the lots of distant worlds that have been discovered, there has been a particular planetary system that has drawn a particular attention, which was the system of TRAPPIST-1. This was discovered by a telescope, by a small telescope actually, only 60 centimeter aperture, on the German equatorial mount with the CCD of the Finger Lakes instrumentation. And funny, this is exactly the same instruments we have on our astronomical observatory here in Salerno. So the same instrumentation was able to make this sensational discovery. So they observed this star called TRAPPIST-1 in 2013, and in 2016 they announced the discovery of 3 planets around the star. But actually, after a great observational campaign involving also some space telescopes, in 2017 they announced that actually there were 7 Earth-like planets around the same star. So 7 rocky planets around the same star. Now the star of TRAPPIST-1 is a very small star. Compared to the Sun, for example, we have a radius which is only 12%, a mass which is only 8% of the mass of the Sun, and the luminosity is much, much fainter. So it's a very faint star. It's called a red dwarf. A red dwarf. So it's also relatively cold with respect to the Sun. And so this star emits mainly in the infrared band, actually. But we can see it only because it's relatively close to the Sun. So it's only 39 light years far from the solar system. And so this is a picture of the planetary system around TRAPPIST-1. There are 7 rocky planets. And in practice, it is possible for all of them to host liquid water, at least on part of their surface. And 3 of them lie in the habitable zone. This E, F, G actually lie in the habitable zone. So this is a particularly interesting system. And furthermore, it will be possible to do further investigations with the next generation space telescope, the James Webb Space Telescope. These are the transit light curves for the 7 planets around the TRAPPIST-1. And it is a funny light curve in which there was a combination of 3 transits. In fact, we have a big drop here when 2 planets passed in front of the star, and then we have another drop here when a 3rd planet passed in front of the star, and then here we are rising back because 1 planet came out of the disk of the star, and then another rise here, and another rise here when each of these 3 planets abandoned the disk of the star. So this is a funny combined light curve which was obtained by the Hubble Space Telescope. Okay, so this is a picture of the system with the 7 planets orbiting around the same star. It's what we have to understand is this is a very compact system. It's very small. Actually, the distances of these planets from the star are very small compared to the orbit of Mercury. I think that maybe one of these curve was the orbit of Mercury, but I don't remember which one. And another interesting thing, for example, one can imagine how the sky would look like if we observe from one of these planets. So, for example, we know on Earth that the Sun and the Moon almost look the same size in the sky. But if we go on TRAPPIST-1F, the size of the star is much larger than the size of the Sun because they are very, very close to the star. The star is actually smaller than the Sun, but they are so close to the star that the star looks bigger in the sky. And this is not a moon, actually. This is another planet. So the distance between two consecutive planets is less than the distance of the moon from the Earth. So this is not a moon, but this is another planet observed from one of the planets of TRAPPIST-1. So it's very fascinating to imagine how this distance will look like. Another interesting property of this system is that all the planets are tidally locked. This means that they show the same phase to their parent star. The rotation and the revolution of the planets around the star are synchronized. Just like the moon with the Earth, the moon always shows the same phase to the Earth. So, in this case, we have the so-called substellar point, which is always exposed to the flux from the star, and the opposite point, and there is an enormous excursion of temperature from the substellar to the opposite point. And in practice, this can be also a good property because we can always find a temperature zone in this kind of planets because the range of temperature is so broad. Okay, also there are studies about the existence of clouds on the substellar points for people who model atmospheres of planets. But now, of course, after we have learned about the mass, radius, distance of these planets, we would like to understand what what kind of chemistry they have. What is the composition of the atmosphere? So we would be very curious to see any signal of oxygen, for example, if the atmosphere can be breathable by any forms of life. And there is a possibility to investigate the atmosphere of extrasolar planets. In fact, if when the planet passes in front of the star, it partially absorbs the light from the star. So if we take a spectrum of the star when the planet passes in front of the star, we will see new absorption lines and new absorption bands which were not present when in the original spectrum of the star. So if we detect this new absorption line and absorption band, we can infer the presence of these atoms and molecules in the atmosphere of the planet. And so this is a technique that has been applied in the case of gas giants, and there has been a partial success, at least in some cases. In the case of TRAPPIST-1, this investigation will be possible by the James Webb Space Telescope. So there is a lot of there are a lot of expectations when the James Webb Space Telescope will become operational, because there will be the possibility to know the composition of the atmospheres of these planets. So this is one of the frontiers of the extrasolar planet field. And in 2017, we organized a school addressed to master students and PhD students about the astrophysics of exoplanetary atmospheres. So this school was held in Vieti sul Mare, close to Salerno, and so Salerno was the center of the exoplanet field during this week, in which we had 80 participants from all over the world. And we also have another organizer here, Luigi Mancini, who co-organized with me this school. And I can also do some advertising. The next edition of this school will take place in 2019, so next year in May. We'll have a new edition, and the focus of the new edition will be the big diversity of exoplanets. Okay, so apart from TRAPPIST-1, there are also many other habitable worlds. And even the closest star to the solar system, Proxima Centauri, actually hosts a habitable planet. So in this case, we have a rocky planet, which is up here, 1.27 Earth masses, and this also lies in the habitable zone. It has been discovered by the radial velocity method. But the problem with Proxima Centauri, it's or flaring star. So sometimes there is a flare, an eruption from the star. So it's difficult to imagine forms of light that resist a lot of UV rays coming to the planet. But anyway, there might be shields on the atmospheres. We don't know. So it may be a very different planet from Earth. But apart from habitable planets, it's also interesting to understand how diverse the planets can be. There are planets which are at the opposite, on the opposite side of the inhabitable worlds. For example, this planet, Celt 9b, orbits a very hot star, a star which has a temperature of about 10,000 degrees. And the temperature of the planet is 4,600 Kelvin. So it's even hotter than half of the stars in our galaxy, even if it is a planet. In fact, this object challenges even the definition of planets. And this also, we also contributed to the discovery of this planet because of the Astronomical Observatory of Salerno. We contributed to the validation of this planet, and it was published on Nature in 2017. There is another planet, WOSPER 12b, which is so close to its star that is already undergoing disruption. So the star is stripping away the envelope of the atmosphere of this planet, which is going to be engulfed by the by the star. But there are actually cases in which we know that planets have been engulfed by the parent star. For example, in this case, we know that this star was a red giant, but now we are observing in this phase, which is called horizontal branch phase. So the star has now shrunk at a smaller radius, and these two objects we observe here are actually the cores of these two planets that survived the engulfment. So when the star became a red giant, it engulfed the two planets and it spoiled them completely of their atmosphere, their crust, their mantle, and only the iron cores survived. And so we are observing here only the iron cores. And also this case is still under debate. This Boyajian star shows very irregular transits. So what is happening here? We don't know. Maybe as swarms of comets, a planet with giant rings, debris, alien megastructures. Even that this was published in a scientific paper because it's a very puzzling case. Now let's widen our horizons. And let's try to make some statistics. We now know almost 4,000 extrasolar planets. We can make some plots and try to understand how planets form, how how common rocky planets are, and so on. So here in this plot we have on the abscissa we have the semi-major axis, so the distance from the star, and on the ordinate axis we have the mass of the planet. And we can even put the planets of the solar system on this diagram, because we have Jupiter here, which is the most massive planet in our solar system, Saturn, Uranus, Neptune, going far away from the Sun. And then the inner planets are here. The Earth, Venus, Mars, and Mercury are here in this diagram. And all these colored dots are extrasolar planets. We can recognize at least 3 clouds here. Here we have a region in which we can recognize analogs of Jupiter. So these are the gas giants. But here we also see that there are gas giants very close to the star, because this distance is less than 0.1 astronomical units. These are called hot Jupiters, like the first planet was discovered by Mayer-Kelos. The first planet around 51 Pegasi was actually a hot Jupiter in this category here. And here we see the so-called super Earth. We have not enough sensitivity to have enough statistics at the Earth size level, but we have a lot of observation of super Earths here, or also mini Neptunes, sometimes they are called. So at least we can recognize these 3 regions here. But what is really astonishing in this diagram is that actually most of the planets of the solar system would be undetected by present methods. So if, our methods can only explore the upper left corner of this diagram, while the lower right corner of this diagram is still unexplored. We don't know how many systems similar to the solar system exist in our galaxy. So there is still a lot to be learned about extrasolar planets. And we need different methods, because the blue dots are radial velocity, the green dots are transits, and they are optimized for closing planets close to the parent star. If we want to go a further distance, we can do that by direct imaging, but this can only be done for very big planets, and microlensing, which is the second topic of this talk in practice. So just a few words about direct imaging. How can we see a planet directly? The light of the planet. The light of the planet is very, very faint compared to the light of the star. So we can only see, we have to block the light of the star with a coronagraph in practice. And after blocking the light of the star, we can see the light of distant planets from the star. These have to be giant planets, and they have to be far from the star and very young, because if they are very young, they have a higher emission because they are still cooling down from their original temperature. So it's only in very particular cases this can be done. Also, the ARMA radio telescopes are observing the protoplanetary disks. So these are planetary systems informations. They are very interesting to understand how planets actually form. But now let's move to the next method, which is microlensing. So this is a method that is based on general relativity, on the very well-known effect of gravitational lensing. In practice, what we do is that we observe a very distant field of stars and waiting for the passage of another star close to the line of sight. When this happens, the gravitational field of this star distorts the image of the distant star. Then what we see is the amplification of the distant star. So sorry for the Italian here, but if we see the light of the star, of the distant star, at some point it will rise because it will be amplified by this gravitational lensing effect, and then in the end, after the passage is finished, it will return to the original luminosity. But if the star that is acting as gravitational lens is also accompanied by a planet, also the gravitational field of the planet will imprint its signal to the light. And so we will also see a blip due to a planet. So this is a way to detect extrasolar planets by the gravitational lensing effect. And there have been several planets discovered in this way, at least 60 or 70, something like that at this point. This is a planet discovered in 2017. In this case, we see the amplification curve of the star, and at some point, if we zoom around the peak, we can see that there is a very distinct picture here, which is a blip due to a very small planet. In this case, I contributed to the modeling of this object, and we discovered that actually it is an Earth twin, but at a much farther away from the star. So it's an icy world with the same size and mass of the Earth. So it's exactly in the lower right corner that we showed before. So this is a very complicated event. In this case, there were two planets, a Jupiter-like planet and a Saturn-like planet, and around a star that was smaller than the Sun. It was half the mass of the Sun. And it is funny to see that this system looks like a scaled version of our solar system, because we have a smaller star and planets close in to that parent star. So we're starting to see analogs of the solar system in practice with microlensing. Okay, this is a quite complicated case with so it's a case of a planet around a binary star, but there are many possible models here. So from the light, it's almost impossible to understand what's going on here. So there are also some cases which are very, very difficult to interpret. This case here is not a planet. Actually, this is a binary system, but one of the components in this binary system was a black hole. So in this case, this is an interesting case in which we are seeing the gravitational field of a black hole and another star acting as gravitational lenses. And we also see the observations taken from Salerno telescope here. So we also contributed to this discovery. Now, one of the problems in microlensing is that we can obtain the same light curve if we even with different masses and different distance of the lens, because the mass and the distance of the lens actually come into the degenerate combination. So only from the light we cannot distinguish the contribution of the mass and the contribution of the distance. Distance and mass are intrinsically degenerate in microlensing. But what we can do is to observe from another point in space. For example, in this case, observations were taken from the Spitzer satellite, which is more than 1 astronomical unit far away from Earth. So observing the same microlensing event from two different points, we will see different light curves, because of course there will be different geometries for gravitational lensing. So in this case, it is possible to break the degeneracy and to estimate with very good accuracy the mass and the distance of the planetary system. So this method has been employed to start to understand, to draw a map of the planets in our galaxy. And our collaborator Sebastiano Cartinovati, who was a postdoc here in Salerno, and now is at Caltech at Pasadena in California. So he's still working on this campaign with Spitzer data. Also, the Kepler satellite was employed for microlensing in 2016. So for 3 months, the Kepler satellite observed the bulge of our galaxy, where the many microlensing events are found. And all the observatories involved in microlensing were active during this campaign, including our observatory in Salerno. The analysis is still in progress, so we're still waiting for results from this campaign. Now, as I told you before, it's very difficult to understand from one light curve what's going on. So if we see a light curve like that with many peaks like that, how can we understand whether this is a binary system, a planetary system, one planet, 2 planets? So modeling, interpreting these light curves is very difficult, and we need a lot of computing power. Furthermore, the problem is highly nonlinear, so in practice there are caustics involved with the formation of additional images and so on. But nevertheless, here in Salerno, we created the fastest real-time modeling platform in the world. So there is a web page in our department web page, which is updated in real time with the models of ongoing microlensing events. So if you go to this page, you will see the ongoing microlensing events that are modeled in real time as soon as new data come in. And also, the code that I wrote for the calculation of this light curves is now publicly available. So in 2016, I made this code for the public, which is something very appreciated from the microlensing community, because it's, as I told you, it's very complicated to model this kind of events. Now, coming to the future. In the future, there will be this mission, WFIRST mission, which is a space telescope that will be launched in 2025 by NASA. And this mission will have two main objectives. One will be the study of dark energy, so the acceleration, the present acceleration of the universe. And the second objective will be the study of exoplanets by the microlensing methods. And so in this case, going from space, it will be the signals will be much cleaner. And so we expect at least 1,000 planets to be found by microlensing. In this case, the sensitivity will be extended to planets in the outer habitable zone, and it will be sensitive to analogs of the solar systems except Mercury. We also expect to find free-floating planets, that is, planets without stars, planets that have been ejected from the planetary system and are now wandering around through space. So there will be, we will aim to deriving the galactic distribution of planets, the remnant mass function, and we will be even sensitive to moons around around extrasolar planets. So in the diagram I showed before, WFIRST will cover the lower right corner, and as you can see, it's also sensitive to all planets in the solar system, not to planets in the solar system, except Mercury. And it will be even sensitive to moons like Ganymede or Titan. So, in the science investigation team of WFIRST, the only member coming from a European institution is me. So I am the only member coming from a European institution. And this is because, as I told you, I developed this code for light curve computation. In practice, I'm involved in the Group 2, development of light curve analysis tools and community engagement, and Group 6, advanced microlensing light curve modeling. So we're pushing forward these efforts for microlensing from Italy. This was a summer workshop we had in 2017 in order to attract new people to the field, because the microlensing community is relatively small. We need newcomers, new ideas, new people working on this field in order to carry these efforts. And just at the conclusion, just a few words about Salerno University Astronomical Observatory. This is an observatory which is on the roof of our department, so not far from here. And it hosts a telescope very similar to the one that led to the discovery of TRAPPIST-1. We are doing support observations for several satellites such as Spitzer, Kepler, Gaia, and TESS. We are a node of the CART follow-up network. And of course, it is also used for teaching in the in the physics master course, and we also hold outreach events with open to the general audience. Okay, just a few features of M42, the Orion Nebula taken from our telescope, the Andromeda Galaxy, a globular cluster M15, and the Ring Nebula M57. So just to show a few pictures taken from our telescopes. So we are at the conclusions of the talk. So as you can see, that there is still a lot to discover about extrasolar planets. We only know one corner of the diagram. We still have to populate this diagram in all the other corners in order to understand how planets form, how many planets there are with characteristics similar to the Earth, and finally understand how common life can be in our universe. So the investigation of the atmospheres, as I told you, will probably deliver great surprises in the next future. And finally, we need to deploy all different methods in order to have this global picture of the field. And finally, as you probably heard from the media, there is also the possibility to, for the first time, people are seriously speaking about traveling to the closest star, Proxima Centauri, at least to send there some nanoscopic probes that will be pushed by lasers and will reach a velocity close to the velocity of light in order to cover the 4 light years from the Sun to Proxima Centauri in a reasonable amount of time. So this is a very nice project that can give you the impression of the point at which humanity has arrived. Okay.
Questions?
Thank you. Very interesting. You talk about making measurements from 2 points in space to decouple mass from distance. Wouldn't it be easier to use another technique to figure out one of the two, like the mass of the star from the luminosity?
Okay, if you mean other methods such as radial velocities or transits, this is not feasible for microlensing events because, of course, we don't have if the planet is moving around this star, the probability that this is also transiting in front of the star is extremely low. Consider that we are that the planet is in a very wide orbit, so the chance alignment of this orbit with the line of sight would be extremely low. And as concerning radial velocities, the problem is that we are looking at very distant stars. So if they are so far and they are so faint, it's impossible to do spectroscopic measurements. And furthermore, the spectroscopic signal would be much below the sensitivity of present radial velocity and present spectrographs. So in practice, this also is not feasible. But there is another possibility to disentangle the mass and the distance to the lens. If we wait at least 10 years from the microlensing event, actually we can resolve the source and the lens as separate objects. So when we observe the microlensing event, we only see one object, which is the source, which is amplified, and the lens that is passing in front of on the line, close to the line of sight to the source. But if we wait 10 years, then we will separately see the lens and the source, and by analyzing the lens, we can understand its mass from mass luminosity relations, for example, from star models. So in this case, it will be possible to understand the properties of the lens independently of the information from microlensing. So this adds additional information and allows a breaking of the degeneracy.
Other questions? I have a question. But it is possible to determine the gravitational perturbation among the planets of the TRAPPIST-1 system because they are very close.
Yeah. Now, in fact, this was one of the first things the people, even the people involved in this code tried to do, because since the system is very compact, the planets are very close to each other, actually are pulling each other in this gravitationally. So they are actually affecting the orbit of each other by the gravitational pull. And in fact, the first simulations that were done about the system of TRAPPIST-1 gave a very odd result. So in practice, they predicted that the system was not stable enough to live for the hundreds of million years. But actually, more accurate simulations were needed to demonstrate that actually the system is stable, because all the orbital periods of these planets are actually can be obtained by ratios of integer numbers. So in practice, all of them are in resonance in each other. So that's why they can be stable. But also the perturbation of the orbits is the key to have the measurements of the mass, because in this case the star is faint. It is too faint to apply the radial velocity method. So the information we have on the mass of these planets come from their mutual perturbations actually. So it was one of the keys to study this problem actually.
Other questions? Curiosity? No. So let's thank the speaker again. The next speaker is Giorgio Biavattene from University of Roma Tor Vergata.
Good afternoon. I am Giorgio Biavattene, PhD of the University of Tor Vergata, and this afternoon I will talk to you about my recent work on testing the Gallavotti-Cohen fluctuation theorem on the solar photosphere. So, the understanding of fluctuation in systems far from equilibrium, but in steady states, is one of the key issues of statistical non-equilibrium statistical thermodynamics, which have some unsolved problems. The fluctuation theorem of Gallavotti and Cohen was introduced in 1995 by Gallavotti and Cohen. It was studied by Kachan. It is valid in systems in non-equilibrium but in steady states. It describes the symmetry features of entropy production rate in this kind of systems. So nowadays, what do we know? We achieve a fair knowledge of systems in situation in equilibrium, but the statistical properties in systems far from equilibrium are not completely clear. A typical example of this system is the Rayleigh-Bénard convection. This is a simulation of Rayleigh-Bénard convection, where the heat transport is maintained by a vertical temperature difference. This is symmetrical Rayleigh-Bénard convection, similar to the convection appearing in the solar photosphere. The background theory. Linear thermodynamics of non-equilibrium predicts that in this kind of systems there is a spontaneous production of entropy. This is connected directly with irreversibility according to the second law of thermodynamics. The entropy production rate can be evaluated starting from the vertical heat flux, J, and the generalized force, Xi. Okay, in this kind of systems, when we are in a dissipative situation, the Gallavotti-Cohen fluctuation theorem assumes these forms, where pi is the probability of finding a positive or negative value of the entropy production rate in a time interval tau. So the Gallavotti-Cohen theorem is valid in a global scale, but it is demonstrated by Gallavotti himself, that this theorem can be also extended to local measurements of the entropy production rate. From previous literature, what we know nowadays is that The Gallavotti-Cohen theorem has been verified in a laboratory experiment by Chang et al. Using, for example, a simple vertical cell filled with water, and they obtained some convection features like this. Other experiments are being carried out by Gilberto et al. In 2004. They use an von Karman experimental setup, which consists in two counter-rotating disks that generates turbulence between them, and in other experiment using wind tunnel. We will compare the results of this experiment with our results later. Turbulent solar convection. In this framework, the turbulent solar convection observed in the solar surface as the granulation, you can see here a movie of the solar granulation, provides an incomparable laboratory to test the Gallavotti-Cohen fluctuation theorem. This is another use of the sun like a laboratory of fundamental physics. We know that the sun has been used to test, for example, neutrinos theory, nuclear theory, radiative transfer theory, and so on. So, this is a simulation of the solar convection. You can see very well the convective cell going up and down in the solar photosphere. This is called the granulation. In this movie, we can see also a vertical cut of the granulation. We see very well a typical Rayleigh-Bernard convection. And these are the simulation of the temperature behavior. We can see that the upper part of the granules are hotter and the intergranular lanes are cooler. And this is the typical behavior of the density in solar atmosphere. This one is a snapshot of our dataset. Our dataset was acquired with the EBIS instrument. This is a very good instrument installed at the Dan Solar Telescope located in New Mexico. And here we present a preliminary analysis of the validity of the Gallavotti-Cohen fluctuation theorem on the solar convection. We are observing only quiet sun region. In solar physics means quiet sun regions, regions where we do not have magnetic fields, because we know that in the sun there are sunspots. The sunspots are the place where the magnetic fields inhibits the convection. So we are selecting only place where there is convection, so no sunspots. Okay, data analysis in the solar convection is a good example of non-equilibrium stationary states, but out of an equilibrium, and following the approach of Chang et al. You saw that I showed before, we can evaluate the vertical heat flux and use the vertical heat flux as a proxy for the entropy production rate. How we can evaluate the vertical heat flux using only line of sight velocity maps and temperature maps of the solar photosphere. To improve our statistics of our data, and especially to test the steady states of the theorem, we compute a running average of Jz over a time step interval called tau. So I will call, for example, J1 is the vertical heat flux for each frame of the temporal sequence of our data. I called J2 the average of the first with the second with the third, and so on. I call J3 the average of the J1, J2, and J3, and so on. And in this case, the Gallavotti-Cohen fluctuation theorem assumes these forms. We have the probability to find a positive or a negative value of the vertical heat flux, and it is proportional to the vertical heat flux itself, and alpha is a parameter to be determined. So, if we perform a simple analysis of our data, we can see how the PDF or the counts of J1, J2, we can plot these, and we can see how the PDF streams going from J1 to J29. I do not perform J30 because I saturate the RAM of my laptop. So this is in agreement with the Gallavotti-Cohen fluctuation theorem. This is I would say a summary of the previous GIF. We can see in black J1 dot, this one, J5, in purple, in blue J10, and so on until J29. We can see that PDFs go shrink. So if we evaluate the asymmetry ratio of our PDFs, so starting from the peak of the PDF, and we perform the ratio of the previous and the sequence bin, and so on for all the dimension of the PDS, and we graphic this. We can see how the asymmetry ratio decreases, so our linear fit goes up, and this is also in agreement with the Gallavotti-Cohen fluctuation theorem. And if we perform a linear fit of the slope of this asymmetry ratio, we can see a linear behavior. And if we decompose our alpha term in a linear term plus a constant, these are the fit parameters obtained by our analysis. You can see there are some discrepancies, and if you want, you can do some questions after. And these are some discussion and comparison. You can see how our results are very similar to the results obtained by the other authors. In Shang et al. In the vertical cell filled with water, they obtained the asymmetric PDS. The asymmetry ratio increased, and these are the plots for the alpha coefficients. They had different alpha, different linear fit for alpha because they vary the Rayleigh number in their experiment. And these are the results obtained by Gilberto et al. You can see the results are very similar to those obtained by us. So, concluding, we tested the validity of the Gallavotti-Cohen fluctuation theorem on the solar surface, especially on the solar granulation. Further analysis of data prepared with Nicole inversion code, which is a more accurate solar software to extract the information about velocity and temperature from spectropolarimetric data, is in progress. Further analysis using the kernel method to improve the statistics of our PDFs is in progress, and this is the first evidence that the turbulent solar convection in non-magnetized regions is a systems in non-equilibrium states, non-equilibrium situation but in steady states, and this satisfies the condition and the symmetries of a general statistical theorem of Gallavotti-Cohen. Thank you for the attention.
Questions?
Is there any analog of this theorem for the magnetic regions? I mean, solar spots?
Yes.
Yeah, so there is an analog.
No, there is no theorem for the magnetized region because we test the validity of the Gallavotti-Cohen theorem on the sunspots. But I think that the validity of the theorem will not respect it because in sunspot we lose the convection because in sunspot there is the buoyancy of the magnetic flux tubes, so that the magnetic fields inhibits the convection, so maybe the validity of the theorem would be disrupted. We will perform this analysis to check the solar convection respects to this theorem.
I know that you are waiting for a question. So I would like to ask you whether your theory can be related to the mixing length theory for convention.
Yes, I don't know this. I don't know if there is a connection with the mixing length. Maybe yes. We can try a test because in this analysis there are a lot of parameters involved because we are testing a general theorem out of laboratory. So you can perform a controlled experiment in a lab, tuning your experimental situation, but the sun, we can only observe the sun. We have to increase our analysis because we have this discrepancy here. This discrepancy is only, if you know, in very long time, approximately 2 thousands of seconds. maybe because you have a typical scale time of the granulation. You see a granule that goes up and then it goes down in a time approximately 5-10 minutes. So if you wait sufficient long time, you lose the memory of the previous granules. Maybe this should be correct.
The theory is no more applicable when the time is...
Yes, maybe we have only a window of time and a window of scale when to apply the theorem. We have to check.
Other questions? Okay, let's thank the speaker again. Our next speaker and last one is Sara Saracino from the University of Bologna.
So good afternoon, everybody. I'm Sara Saracino, and I just finished my PhD at Bologna University. And today I'll try to present you how bulge globular clusters look like once they are observed with the multi-conjugate adaptive optic system. So this is the last talk, so we are very few, and I hope not to bore you too much. So let's start with a brief introduction on the galactic bulge and its globular cluster system. So the galactic globular clusters are among the oldest stellar aggregates in the universe. They can be as old as the universe itself, and in particular they are systems of 10 to the 5, 10 to the 6 gravitationally bounded stars, and they are useful, so they are very often used as good tracers of structural and physical properties of different components of our galaxy, like the halo, the bulge, or the disk. But in particular, the galactic bulge is one of the most inaccessible regions of our galaxy, due to thick clouds of dust which almost totally absorb the optical light. In this sense, from a compilation by Vika and collaborators in 2016, we found that the galactic bulge hosts a significant fraction of the globular clusters in our galaxy, but due to observational limitations, they have been systematically excluded from large surveys, and so they remain purely studied so far. So when we want to study the stellar population of a globular cluster, the first thing that we want to do is to get a color magnitude diagram for this for all the stars in this system. From this color magnitude diagram, we can derive the age, the metallicity, and the many other properties of these stellar systems. So these are the color magnitude diagrams that we get so far for these globular clusters. Probably you are not so familiar with the color magnitude diagram, but you can trust me that all these color magnitude diagrams are not so deep, because they just sample only the very bright part of these color magnitude diagram, and so we cannot infer something about their age, because we cannot reach the main sequence turnoff, which is an important feature for this stellar system. But now the question is, can we do better? And probably we have a solution, and it can be adaptive optic systems, because they provide both an high angular resolution, which is fundamental when we want to resolve individual stars even in the very center of these crowded regions, but also near-infrared wavelengths where the extinction drops out. So adaptive optic systems provide both these ingredients at the same time. And so just very few key concepts about adaptive optics. So when the light of a star or any other astronomical object passes through the turbulent Earth's atmosphere, its wavefront, which is initially flat, becomes distorted. So the spatial resolution here is completely lost. I don't know. The spatial resolution of the images that we can get is completely lost. So this effect can be solved, and a possible solution is to apply adaptive optic systems. So the basic concept is the following. So we have a wavefront sensor which analyzes and in real time the wavefront coming from a star used, a very bright star used as a reference, and it corrects in real time using a deformable mirror the wavefront coming from these objects that we want, from all the objects we want to observe. And in this sense, the spatial resolution is restored. So in some sense, we can apply this technique to observe every kind of objects in the sky, but adaptive optics can be used also in medicine or in biology, and it has many other applications. But from this very basic concept, I want to make a step further, and so to go from simple adaptive optic to multi-conjugate adaptive optic systems. And I want to show you the case of GEMS, which is this instrument mounted at the 8-meter Gemini South Telescope in Chile, and it works using 3 natural guide stars and 5 laser guide stars to compensate for the blurriness of the Earth's atmosphere, and it works in tandem with a high-resolution near-infrared camera, and so even from the ground we can reach the diffraction limit. So we have seen we are on the ground, but we can get very interesting results. And so in this context, I want to show you our project with this system. So the idea is to try to observe a sample of obscure and massive globular clusters located in the bulge using high angular resolution observations and at near-infrared wavelengths. And so during the last slide, I will try to see you how many applications there are, and in particular, we can unveil and explore systems. I'll present you the case of LILER-1 to perform deep and accurate near-infrared observations as for NGC 6624, but also we can test astrometry using ground-based telescopes, because up to now only space observations have been used for astrometric studies. So let's start with the first one, which is LILER-1. LILER-1 is a very interesting object in the galactic bulge. It is located very close to the galactic plane, and it is highly extincted with an extinction of 10 magnitude in the optical band. In particular, it is important for many other reasons. For example, it has the second highest stellar encounter rate, which means that the collisional, so collisions among stars are highly pronounced in these globular clusters. And also, Tam and collaborators in 2011 revealed an intense gamma ray emission coming from this system. So here I want to show you a comparison of how a very central part of LILER-1 looks like when it is observed with ground-based observation. So both are using ground-based observation, but not assisted by adaptive optics and using the Gemini NCAO system. So as you can see here, you can actually resolve individual stars even in the very center, and even if this cluster is highly extincted. So the improvement in terms of angular resolution is remarkable. And here is just a picture, just an image that you can get, but here from a scientific point of view, we want to derive the color magnitude diagram of this cluster and to compare it with the previous works. And these are two color magnitude diagrams obtained from the space and also from the ground in the optical and near-infrared from previous literature works. And this is what we get in terms of color magnitude diagram from these Gemini observations. So these red boxes are so indicate the same parameter space in color, both in colors and magnitude. So you can see that here all the evolutionary frequencies are well distinguishable. And here I just plotted the name of different evolutionary sequences that we can recognize in the color magnitude diagram. But yes, from this picture we can just understand that we can go much deeper. So 3 magnitudes below the previous works, and also we can start see the main sequence turn off. That is the feature that before I told you can tell us something about the age of this cluster. So this is just promising results, but also for the possibility we had to resolve individual stars even in the very center, we try to derive the star density profile of the cluster in order to infer something about the structure and the physical properties of these systems. And so we derive that it is actually significantly less concentrated and less extended than previously thought. But we derived also its mass, and it is quite massive, with a mass of a few in 10 to the 6 solar masses, which is comparable to the most massive globular clusters in the galaxy. And we also confirm that it has a high stellar encounter rate. So just to make a summary, Linear 1 is an ideal environment for the formation of collisional objects, like, for example, millisecond pulsars. But so far they have not been identified because the dispersion measure is so high, so we cannot distinguish, and so we cannot see really millisecond pulsars in this cluster. But we can think about their presence here. So now let's move on the second case, NGC 6624. A well-studied cluster in the optical band is very different with respect to the previous one. It is located at the edge of the inner bulge, and it is just a low reddening cluster because it's 0.3 compared to the 3.1 of the previous cluster. And it is in a post-core collapse state. Which means that it is a dynamically evolved cluster. All the more massive stars have been sicked in the center, and all the light stars are in the outskirts. So here a comparison of how these observations in the near infrared look like compared to HST observations in a different band. So as you can see here, the spatial resolution is quite comparable, but we have to think about that in a diffraction limited regime, when we are at the same wavelength, the spatial resolution with the Gemini can be more than 4 times higher than in the HST, just for the difference in the diameter telescope, so in the collecting area. So this is the color magnitude diagram of this cluster, and it looks quite different with the previous one. So here you can really see all the evolutionary sequences, and you can also infer, so you can also derive this very peculiar feature, which is a knee, and there are very few globular clusters in which up to now we can really see the main sequence knee. And it can be useful also to as a second as a second anchor to derive the age of these systems. And I want to stress that this is the deepest and highest quality near-infrared photometry that we get only using ground-based observations. And so the age is important in for this cluster we just try to compare theory with observations. So we used state-of-the-art stellar models to derive the age of this cluster using a chi-square minimization and an isochrome technique, which is basically you can try to get the best fit of these regions, so the main sequence turn off and the subgiant branch, which is somewhere here, and we got an absolute age for this cluster, which is of about 12 gigayear. So it's really hot, but is quite expected for these kind of clusters. And we also derived for the main sequence stars because we were able to go down to masses of 0.4 solar masses. We derived the luminosity and the mass function of this cluster in 3 different radial beams. And this radial variation that we observed in both functions is the first direct clear indication of a mass segregation in this cluster, where actually all the more massive stars are sitting in the center and the light ones are in the outskirts. And I go through NGC 6569, which is an intermediate cluster between the previous one and the NGC 6624. And this is a moderately extinct cluster, which is located very close to the previous cluster, but it has a metallicity. It is not so metal-rich as typical for globular clusters located in the budge, but it has a sizable population of variable stars, which is quite peculiar for these kind of globular clusters. And for this cluster, we derived to combine, so to have a multi-wavelength approach to combine optical and near-infrared data to try to get the best from these observations. And just for so when we look to these observations, so to this color magnitude diagram, we saw these peculiar blue horizontal branch stars, which was was an unusual feature and was not expected. So now the question was, is it real? And the only possibility to answer to this question is to try to distinguish cluster stars, so cluster members, with respect to fringe stars. And so the only possibility we have is to make a proper motion cleaning of this color magnitude diagram. But when we want to make this kind of study, we need to have two very flat and distortion-free reference frames. But this is not the case of our GSAOI camera, because it's highly distorted and with a distortion up to about 0.8 arcsecond in all the 4 chips that constitute this camera. And so this is a quite new instrument with no solutions to correct for this effect were published. So we decided to do this by ourselves, and so this is the first analytic solution for geometric distortion of the camera, and so we get an accuracy of 1 milliarcsecond. And we try to test this solution in our for these clusters, for 65, 69, and we saw that it works really well, because we combined Gemini observations as the first epoch and HST observations as the second one, and we derived the relative proper motion of for the stars in this cluster. And so here is the total of the stars, and in red are all the stars that are can be considered as still stars, and so here it remains with only cluster members or highly probable cluster members. So we can actually clean our color magnitude diagram, and so we see that only also after this proper motion cleaning, a few blue horizontal branch stars still survive. So they are really member of this cluster. But in this highly esteemed cluster, there is not only the problem of reddening as a whole, but also the differential reddening in the field of view of the cluster. And so even if it's quite small, you can get some differences that can affect your color magnitude diagram. So here you can see the color magnitude diagram, the original one, so before the correction of for differential reddening and after we apply the correction. As you can see here, all the evolutionary sequences are much better defined, and we derive a delta ADB Menvu. ADB Menvu is a way to define the extinction that is of about 0.1 magnitude in this very small field of view, I have to say. And also for this cluster, we derive the age using the technique similar to the previous one, but also using Monte Carlo Markov chain simulation to derive the uncertainty on the age, distant modulus, and extinction. And so we get for this cluster an age of 12.5, 13 gigayear with an uncertainty of only 1 gigayear, which is quite is quite low. So this age is quite well constrained. And here, just the conclusions. I leave you this, with this conclusion, and I hope that I convince you that adaptive optics can be really useful for in our near future, when very ground-based telescopes will start to appear as ELT or other ground-based telescopes, and so we can try to do the best that we can with these instruments. And so I just finished. Thank you for your attention.
Questions?
A very interesting talk, and I had several questions. I tried to be synthetic. So, first about the extreme horizontal branch stars that you showed. actually, they are not so rare. They are observed in several globular clusters.
Yes.
Even the M15 that I
Yes,
showed
yes,
before,
but in
it
the,
has an extreme horizontal branch like
yes,
that.
but in the galactic bulge or the globular cluster are somehow meta-rich. And so you can just expect a very red clump, is not so extended the horizontal branch. And also in this globular cluster, so people in the literature thought that is just a metal-rich globular cluster because it has only this red clump here and the horizontal branch stops here. So this is something new for this globular cluster, but not in general because we have very extended horizontal branches, much well populated than this. So this is not as a general.
Yeah, but you told that it has actually a lower metallicity with respect to the others that you studied.
Yes.
Are you also fitting for metallicity in the isochrone fit?
No, in the isochrone fit, I fixed the metallicity to the most recent value. And for example, for this cluster, there is a work of 2018 which define from spectroscopic studies the metallicity of this cluster. So we can rely on this metallicity because when you have many free parameters, you can have many degeneracy, so you cannot distinguish really what is going on.
Yeah, particularly in the infrared, probably with this degeneracy cell, maybe worse.
Yeah, yes.
Yeah, and in the first color magnitude diagram you showed for the highly extincted cluster, there was the disk main sequence.
Yes,
yeah. But there is also a lot of stars which looks like another main sequence there.
Yes.
What's that? Is that a contamination from bulge stars not belonging to the cluster?
No, this is an open question. It's a very good question because because the bulge or red giant branch and a main sequence exactly overlap the one of the cluster. So this is not not populated by stars in the cluster in the bulge. But of course can be some blends, but cannot be so bright. So the possibility is that they are cluster members.
You mean blue stragglers?
Blue stragglers, but they are too high. So they are too much and they are too bright. And of course, you cannot say what is the percentage of blue straggler with respect to the other stars. But so we just took the spectra of some stars in this blue plume to try to see if they have the same metallicity of the cluster, if they look something different. But our idea is that it cannot be a purely background feature, because can be the disk, so the other part of the disk, so we try to use many explanations, but it's still, so it is, and another important thing is that this star seems to be centrally concentrated, more centrally concentrated than fixed stars. And so why I can understand that they are centrally concentrated in the cluster center if they are not member of the cluster.
This
So
goes to the blue stragglers explanation.
Yeah, but not so they are too much.
Yeah. And you also look for millisecond pulses. Have you also looked for the low mass X-ray binaries, which are also other collisions?
Yes, no, this is not the work that I did so there is another student that did this work, and he couldn't find any reliable measure of millisecond pulsars or low mass X-ray binaries or something, because the dispersion measurement is so high, and so the background is so high, and you cannot rely on the results that you get.
Thanks. If there are no other questions, we can ask this again. So, now there is the second annual IPM meeting.